Well, thank you very much, Osa, and thanks very much for the invitation to come and give this inaugural seminar in the series here at KTH. I'm really honored to be invited to do that. As you can see from the title, I'll be talking about this concept of the Anthropocene, but going beyond the concept itself to discuss what this means for sustainability. And I'll say right at the outset that most of the action and interest in sustainability occurs at smaller scales, as it should. It occurs at local scale, regional scale, and maybe up to the scale of a country or so on. But quite often, people don't think of the global scale, and that's because we've always assumed, for most of our existence on the planet, that the global scale is a given, that the global environment is stable, we don't have to worry about, we worry about things close to home. Well, that's changed with the concept of the Anthropocene. So I'll focus on that first, and the second half of the seminar will be, well, how do we solve this global scale sustainability problem? How do we deal with the Anthropocene? So let's see if I can get the equipment's working perfectly. So that's the title of my talk, and we'll go right to the first slide, the Anthropocene. As you can guess from that word in English, it has two parts. The second part, the scene, the C-E-N-E, is reminiscent of geology. You may have heard of the Pleistocene or the Eocene and so on, which are geological time periods in Earth history. And geologists use that because it's a useful term to look at changes in how Earth has evolved. But the first part of the word, the anthropo, is really the interesting one because it refers to us. It refers to humans. And basically what the word says is this is a new geological time period, a new geological epoch. But it's not one that's driven by natural, so-called natural changes, the great forces of nature. It's actually driven by humans. So let's go through a little bit what this actually means. As I said, it's a geological term, so I'm trying to put in these four panels, put it into perspective. These are four increasingly short time slices. First one is about 65 million years. Just to show you, the Earth has been very much warmer than it is today, and it's actually been in ice-free states previously. But it's the last three that are important. This 3 million one, that's part B up there. You see so many wiggles in that, ups and downs. Those are oscillations between cold periods, ice ages, and between warm periods like the one we're in now. That's actually important because that's the time period in which our species developed. Now, we're actually much more recent than that, but early hominids go back to 2 or 3 million years. So our genetic code has developed during that time period. Then we have 60,000 years, and then the last 10 or 15,000 years. And those last two, C and D, I want to go through in more detail separately, because they really are part of the Anthropocene story. So here we have about 400,000 years, not quite 500,000 years. This is an Antarctic ice core, so it's a reasonably good resolution. The one I want us to focus on is this middle red line here that I'm highlighting. That's a proxy for temperature, and we can see quite clearly then the regular pattern of ice ages. That's these low bits, very jagged line there, very erratic, and then the very short warm periods in between. Now, this is important because our species, fully modern humans, evolved about halfway through this record, about 200 and some thousand years ago in Africa. So we've lived through two of these cycles of ice ages and warm periods, but this is what I want to focus on here. This is the present geological epoch. It's called the Holocene, and you can see it's a little bit longer, in fact, quite a bit longer than the other ones, and there's a good reason for that. It has to do with the orbit of the Earth around the sun. But the important point is, throughout all this history, we've only been hunter-gatherers. It's only here that we developed agriculture. So let's take another look now in more detail just here. And to do that, we'll go to the other part of the planet, to the northern hemisphere in Greenland, and we'll look at a Greenland ice core, which is here. Now here you see, at least in this part of the world, the ice age was very erratic. There were very spiky warm periods and then drops back down into the ice age. So it was very tough for humans living up in this part of the world. But here's that long warm period now. You can see it's about 10,000 years long. And compared to the ice age, it is a very steady climate. It has allowed us to develop agriculture, which started about here, and then villages and cities, and then building up to civilizations in many continents, and of course now our more globalized contemporary civilization. So this period here, it's hard to read that because it's in red, is the Holocene. So that's the most recent geological time period in Earth history. And this is the one that we propose that we are now leaving, and we're going into a new one called the Anthropocene. So let's talk a little bit now about what that actually means. There's been a lot of work done on that, and a lot of it involved Paul Crutzen, who actually first used the term in the year 2000, and other colleagues that I've worked with over the past decade or so. Now, most people think of climate, and indeed climate is really important in defining or describing geological time periods in Earth history. And the present one, people are starting to sense that the climate is shifting. These three pictures are pictures of extreme events or the consequences of them. They were all taken in the last 3 years, and they all come from Australia. So we have a bushfire, we have a flood, and we have a tropical cyclone. We have those anyway, but we have good evidence in Australia that the nature of these events is changing. This is focusing people's attention on changes that are occurring. But of course, the Anthropocene means much more than climate. Here's an example of a much clearer human impact. This is on marine ecosystems. This line here I'm showing you is the catch of codfish in the North Atlantic. And you see for a long period it was slowly creeping up, and then just after 1950 the catch went up hugely, and that was because we developed mechanized ways to catch these fish. Basically the fish didn't have a chance. And we forgot, of course, that we were working with an ecological system that had limits, and so we exceeded the limits, and the population crashed, recovered a little bit, and around 1990 crashed down close to zero and hasn't yet recovered. This is an example of a direct human impact on the Earth system, in this case, fishery. But we're terrestrial creatures. We live on land, and we've affected land even more than the ocean. We've changed vast areas of the Earth's landscape. This is a completely industrial landscape. It's been made over by humans, new species planted in rows. We've straightened out the river and smoothed it out and so on, because we want to derive direct benefits from that landscape, one of which is food. But speaking of food, we've also changed terrestrial ecosystems all the way down to the genetic code. And now we're producing new types or modified organisms that were not through evolution, but through direct human change of genetic code. So massive impacts all the way around terrestrial ecosystems. And we've affected material flows around the planet, too. This is an interesting one because it's not really a flow. It's what we call virtual water. What we're measuring here is actually the trade in grains or cereals, things like wheat and rice and maize around the world. But embodied in them is the water it took to grow them. So in effect, we are exporting water from one place in the world, and of course in places where they don't have much water, and you can see where a lot of these arrows end up in the Middle East, they need to import water in the form of food that's grown with water. You see, a lot of it comes from North America, and interestingly, there are a couple of big arrows coming from my country, which is the driest inhabited continent on Earth. So we don't have much water, and we're shipping a fair bit of it out, which is now actually a cause for concern down in Australia. But this is a massive change from most of the time when humans were on the planet, where we sourced our food from the place we lived. When you put all that together, you can look at material flows. This is actually now a real material flow. This is nitrogen. Pre-industrial, post-industrial. Look at this huge arrow which didn't exist. That's industrial fixation of nitrogen. You don't need to look at all the other arrows. It just tells you that we have massively changed how the nitrogen cycle operates, more than we've changed the carbon cycle. In terms of the water cycle, these red dots are the areas where there are large dams. And when you look at that, look at all these red dots around all the continents, you'll find that every major river on Earth, apart from a couple in Siberia and some in Canada, do not flow unimpeded to the ocean. Okay, that's a huge change in how the hydrological cycle operates. And we divert about half of that water for human use. And some of that, after it's used, finds its way back into the ocean, and some is evaporated back into the atmosphere. We can look then also at the land surface and where we grow our food. These colored areas here on this panel show the areas that are dominated by cropland. And it's about 13 or 14% of the Earth's surface. But much of that surface, like Australia down here and like Siberia up here on the top, are either too dry or too cold to grow food. So most of the areas that are suitable in terms of soil and climate have already been converted. There's very little more we can convert. The only areas left are the tropical forest in Amazon and in Central Africa here. And of course, we don't want to forget about climate. It's very important. I talked about extreme events. This is a very big cyclone coming in on Australia. And of course, the one that everyone thinks about is the global average surface temperature around Earth. And you can see that since about 1970 here on this graph, there's been a steady increase in that temperature, which continues to this day. So that's a very quick picture of what we call global change, arguments that we're now leaving the Holocene. When I was working here at Stockholm as director of the International Geosphere-Biosphere Program, we decided we really wanted to quantify what the Anthropocene was all about. So we published this a couple of years after the millennium, after 2000. And what we're trying to do on each of these little graphs, and you can see that each of the 12 have a time axis from 1750 to the year 2000. That's to pick up the beginning of the Industrial Revolution through to close to the present time. And in each one of these, we look at some aspect of what we call the human enterprise, human activity on Earth. Now, each of these is a global aggregate, and that masks a lot of changes between developed, developing countries, parts of the regions around the Earth, and so on. But there's population. These are estimates of economic activity, GDP, and foreign investment. Here's resource use, damming of rivers, water use, fertilizer. Here we have urbanization, paper consumption. This is the indicator we use for globalization, McDonald's restaurants. It turns out to be a really good indicator. It correlates well with growth in trade, for example. And then we have transport and communication. Now you can see the shape of all 12 of those curves. They're all going up, and they're all going up fairly sharply. But one thing I want you to note is the year 1950, just the one mark in on all of those. Something dramatically different happened to us after the Second World War. And in all of these curves, the slope changes at 1950, every one of them. And in many of them, like McDonald's restaurants, international tourism, transport, motor vehicles, there was no significant activity before 1950. It's a period we now call the Great Acceleration because there was an explosion of human activity. I'll show you just how dramatic that is a few slides in. All right, so that's the human part of it. And you'd say, well, that's interesting, but what does it matter for the environment? So the second part of the picture is doing exactly the same thing in terms of 1750 to 2000, saying, how can we measure the impact in the environment? Now, again, these are global aggregates, okay? So again, it masks big changes regionally and so on. But nevertheless, because my emphasis here is global, the Earth system, this is an important thing to look at. So the top three are the famous greenhouse gases, and the most famous one is in the upper left panel, which is the CO2 concentration. Again, you see it going up, but again, you see it going up more sharply somewhat after 1950. Ozone depletion in the stratosphere is this one down here, second one on the left. The two panels here on the second row on the right are the only two that are directly climate. It's temperature and the number of large floods. The bottom six panels are all to do with ecosystems. In terms of modification of marine ecosystems, the one on the right here, just up from the bottom, is the amount of nitrogen going through the coastal zone. Look at 1950 again, absolutely sharp change. The bottom three have to do, or the bottom two on the left, have to do with land ecosystems. The one on the lower left there is the amount of tropical woodland and forest that is being lost, being deforested. And the last one on the lower right is really important. This is the extinction rate in terms of global biodiversity. Not much before 1900 and accelerating again after 1950. Now, each of these panels shows changes that goes beyond the Holocene variability. So this, in summary, is the evidence from scientific research that the Earth is moving out of the Holocene and into a new epoch. And in each one of those 12, there is very strong evidence that these are not natural variations, that they are driven by the human activities we summarized on the previous slide. So these two slides together, in a way, put forward the evidence for the fact that we've left the Holocene and we're going into the Anthropocene. So climate is certainly important, but as I've shown here, it's much more than climate. Now, I told you there's a very good way to look at that great acceleration, and the American magazine National Geographic did this last year. And they did it this way. They looked at this equation here, the impact of humans is population times affluence times technology. In other words, how many are we, how much do we consume, and what technology do we use to make the goods that we consume. So that's three terms here in the equation. So we have three axes here. This is population, that's technology. The vertical one is affluence, a proxy for how much we consume. You might be able to see a tiny little wedge right down in the bottom of this box. It's hard to see on this figure. That's 1900. That is the size of the human enterprise in 1900. Okay? You might see a little one just above it. That's 1950. So in half a century, from 1950 to 1900 to 1950, we only increased the size of a box a little bit. The huge big box is 2011. So in little more than the next half century, we massively increased the amount of stuff we produce and consume. That visually is the great acceleration. And that really is what's pushing the Earth into the Anthropocene. We'll talk about equity issues I've got up there in a few slides. Another way we can look at this is using an analysis called global footprints, which is actually looking at each one of us and say, how much land and how much sea does it take to produce what we consume? For example, I just had lunch before I came here, and I had some cod, okay? So how much ocean did it take to produce the cod that I ate? How much land did it produce how much land did it take to produce the rice that I eat, and so on. You can do that for each person depending on their diet. How much CO2 did I emit by flying from Australia to Stockholm to give these talks? That has to be absorbed somewhere. So you can calculate a footprint for all of us. So when you do that, and you can measure it in terms of the number of planet Earths when you add up for 7 billion people, what our footprint is. We started doing that in 1960, and we were consuming about half of planet Earth. Somewhere in the 1980s, we crossed 1 planet Earth. In other words, we were consuming the entire area of Earth. Now we're up in 2010 or 11, we're up about 1.3 or 1.4 planet Earths. You say, how can you do that? There's only one. Well, the answer is we're eating into the natural capital. We're not just living off the interest. In other words, we're not living off the productivity year by year of the Earth. We're actually starting to undermine that by taking out some of the Earth's capacity to produce into the future. It's like if you have a big endowment and you're living off the interest. And you can live very well off the interest. But then you decide, we want to live a bit better. So you start actually using the money in the endowment. You can live really well, and might live really well for quite a while until the endowment runs out. So basically, we're eating into Earth's endowment is what's happening now. This is where the equity issue comes in. We've combined two things here. There's the global footprint on this vertical axis, and that's the number of global hectares per person. It's a little under 2. So each one of us is allowed only about 2 hectares of land and sea combined to produce everything we need and to absorb everything we give off as waste. This horizontal axis running along the bottom here is a thing called the Human Development Index, or HDI. It's a basket of indicators about how well off we are. It has to do with income, but it also has to do with infant mortality, life expectancy, some health indicators, and so on. So you want to be over here to the right, and it's assumed that once you get past 0.8 on this indicator, which goes up to 1, you have a good level of human well-being. But of course, this line here is 1 planet Earth, this broken line we put across here. So this little shaded in square in the bottom right is what we call the Sustainable Development Quadrant. And you try to get in there. All of these dots are countries. We can measure their HDI, we can measure their footprint. So here you see the poor African countries, which are way down in terms of well-being, but they're also well under 1 planet Earth. They don't consume much, but they have a low index of well-being. Here we have the wealthy countries. There's the United States. There's one of the Middle Eastern countries. I think that's Saudi Arabia, but I'm not sure. Might be one of the smaller ones. And all of the developed countries are up here. We're doing pretty well in terms of well-being. We have good lives. But we consume far too much, way above one planet Earth. The US is about 4.5 or 5 planet Earths up there. European countries are the light green ones. So Sweden would be down here. Far to the right, it has one of the highest human development indexes in the world, but it's still consuming too much, about 2.5 planet Earths. Australia's up higher. We're the brown one up in here. I think we're the brown one right there. So here's the problem. You can see a curve developing. As countries develop, they move up here. And they improve their well-being, but they do that by consuming a lot. In fact, consuming too much. So there's the dilemma. We want to improve human well-being, but we have to stay in this bound. In a nutshell, that's the sustainability issue. To achieve sustainability, you have to have a sufficient level of human well-being. And we can do that. What we haven't learned how to do that is to do that within the limits of planet Earth. And that's really the challenge that we face. So that's a quick tour through the Anthropocene. What I want to do in the second half of the talk is look ahead now and look at this challenge of sustainability and see where we might be going. So the Anthropocene is changing quite dramatically in the 21st century. Are we headed towards sustainability? There's a lot of talk about it. Or could we be headed toward collapse if, in fact, the life support systems that deliver ecosystem services to us, if we erode them too much, if we destabilize the climate too much, will we collapse? That's the big question for the 21st century. Where are we really headed? So let me just give you some thoughts on where we might be headed. Here are some trends only over the last decade. Those graphs I showed you of all the human enterprise going up and so on, that was driven by 20% of the human population, the wealthy countries, the OECD. That is changing very rapidly. We now have rapidly developing countries, China, India, Brazil, South Africa, Indonesia. They're beginning their own great accelerations. Their consumption is going up and so on. And legitimately so, because they're trying to bring people out of poverty. The world is reaching what we call hyperconnectivity. We're so connected that an instability in one part of the world propagates very fast. Think global financial crisis. And now we're reaching some peaks of resources. I'll talk about peak oil in a moment. Everyone's heard of it. But you may not have heard about peak phosphorus, which is being debated. And why is that important? An absolutely essential element in our bodies, and we need to get it through our food supplies, and we use it in fertilizers. But there are arguments that that's not limitless either, and we may be running out of the easily accessible, easily mineable phosphorus. I left this one at the top because I want to follow it with another slide. And that has to do with biodiversity. There's almost a breakthrough. We've constructed an artificial chromosome, the actual genetic basis of life. We've inserted it into DNA, and we've actually put it into a bacterium, one of the most simplest forms of life. And it's actually stayed and modified the behavior of that bacterium. So we are very close to synthesizing life. Now that has taken tens or maybe hundreds of millions of US dollars to do it, and a big army of scientists to maybe affect one small bacterium. But the next slide is the other side of the coin, as they say. And this is looking at extinction rates around the world. So the background rate is here. It's given from maybe 1/10 to 1 extinction for every 1,000 mammal species for every millennium. So think of 1,000 mammal species over 1,000 years, one of them goes extinct. That's the natural background rate. Right now, we are sitting here. These are estimates of mammals, birds, and amphibians, up at 100 times or perhaps 1,000 times more than background. Huge increase. We're losing species at a vastly larger rate. And this is where we may be going in the 21st century as climate change kicks in, another factor of 10 or 1,000. So here's the irony. We spend millions of dollars and tens of scientists' time to make one chromosome that might work in a bacterium. And at the same time, we don't devote the resources to turning around the massive loss of the genetic heritage that we already have out there on the planet. And I think it's one of the most ironic features of the 21st century. And it's an example of the Anthropocene. I talked a little bit about peak. There's peak oil. the estimate of what we might be able to produce. These are done by companies or industry associations. So it's the oil industry itself estimating how much it has left. When you look at all these curves, by the time we get to 2025 or 2030, they're all going down or they've all plateaued. So we've pretty much hit peak oil. That doesn't mean it's going to disappear tomorrow. It means it's going to be very hard to push production much higher than it is today. And that's important because demand keeps going up as these large countries like China and India develop and put more demand on petroleum products. Now, there's a really interesting consequence of that we've already seen. I'm showing that in the next slide. Because of this fact that demand is now outstripping our ability to produce, we're seeing price spikes. So this graph here shows, the top one, shows the crude oil price. And it's really hard to see the timeline. This is the year 2000, and this is 2011 over here. So you see the price creeping up, and then you see a big spike that occurred just at the end of 2007 into 2008. And then, of course, it became expensive. So people didn't use so much, price dropped. And then it started creeping up, and it's dropped again in 2012 a bit. But the point is, each time it does that, the base price is going up. That's the supply-demand problem. All right, it affects how much you pay if you take your car in and fill it up with petrol. But it also has some other fundamental consequences. This is the price of food, the FAO Food Price Index from 1990 to 2011. So if we start at the year 2000, which matches the beginning of that graph, you might see some similarity in the graphs, okay? That's the price of food. So we have a fundamental connection between resource constraints and what people actually need to survive. A very, very close correspondence. And so the so-called food crisis back in 2007 and 2008 was very tightly linked to the price of oil, because oil is ubiquitous right through the food systems, to drive the tractors, to use in the processing plants, to transport the food, to refrigerate things, and so on and so on. So there's been some interesting analyses of the global food crisis. And what we can say is that just like the financial crisis, it spread extremely rapidly around the world. It had a powerful global scale driver, the price of oil. But then other things happened too that contributed to it. There was pro-biofuel policies at the same time, particularly in the US. Maize was diverted into ethanol production, okay? And that took more food out. I didn't put it down, but down here, but at the same time, we had a severe drought in Australia. Our food production went down. The interesting one here, though, was a reactionary protectionism. The Russians were worried about the price going up in their country. They stopped exporting, and that drove the price up even further. So here you have a strong driver, price of oil, but lots of other things happen to add on or make the problem even worse. So it's a good example of a rapidly expanding problem, strong underlying global driver, then other things, reactions happening to exacerbate or make the problem even worse. And we should see more of this in the 21st century. All right, the Anthropocene, where are we now? Formal status, it's actually being considered by the geologists. They're debating it because they need to decide whether formally we're going into a new epoch. What I've said, I'm on the working group, by the way, that's doing this. What I've told them is you can make your decision based on sediments and so on, but the term will continue to be used throughout many other areas of science, social science, and indeed policy, because it's useful. You can argue about where it begins. I think it begins at the Great Acceleration, middle of the 20th century. But I want to talk about, in the last part of my talk here just now, is the duration, because this is completely different from any other geological epoch. All the other ones have ended. Geologists always looked backwards and said, here's the beginning and here's the end. What's making it difficult for them is we're in the middle of it. It's unfolding as we talk, so we can't see an end. We think we can see a beginning, but we can't see an end. And the end depends upon us, and that's, again, the sustainability issue. The Anthropocene could last for thousands or millions of years. If you look at it in terms of biodiversity, like the time the dinosaurs lost, that was actually the end of a time period in Earth history. It takes millions of years for species to build back up. So the Anthropocene could really be around for a very long time. Okay, let's go back to where I started and talk now about where the Anthropocene might be going. That's the graph I showed you. of the Vostok ice core, the Antarctic ice core, temperature going up and down between ice ages. Now I'm going to apply a little complex systems thinking. If any of you have taken courses in complex systems, there are some particular characteristics that systems as a whole have. The Earth as a whole acts as one system at this level. All right, we talked about two states. There's one, that's the glacial state, the cold state, and of course the warm periods. So think of it as two different states that the Earth moves between in a fairly regular way. But there's more to it than that. There's something we call limit cycles. Let me show you what that is. The bottom one is methane gas. Look at how it oscillates also between warm periods and cold periods. But the point is, there is a floor and there is a roof that are fixed. The same is true of temperature. There is a floor and there is a roof that is fixed. I think I missed, let's see if I can get the other ones up there. No, they're not coming through. Yeah, they are in reverse order. That's the floor and roof on temperature. And there's one on carbon dioxide that we don't see. What I've done here is I've put an arrow here that's hard to see on the right. This is where we are now. This is an accurate ending to the arrow. So we have massively changed the limit to carbon dioxide. We've done the same thing for methane. Yeah, that's coming up. That's how much we've changed methane. So if you look at the Earth as a system, these changes in gases are really big, and they're very important. And what we've done is broken the limit cycle in this complex system. We're starting to break the limit cycle in temperature because it's responding. Here's a 2,000-year temperature record, lots of oscillations, but this red line is that line I showed you at the beginning of temperature going up, put on that same time scale. So temperature is now starting to break its limit cycle. Again, this is evidence that we've moved out of the Holocene, which is the end bit of that ice core data that I showed you, and into the Anthropocene. But it really has implications for the Anthropocene. I'll just go back and show you this graph again as a point of reference. This is this is AD 200, time of the Roman Empire, and here's today. So it gives you about a 2,000-year time slice. Now, if we go here, what I'm doing is I'm taking exactly the same graph. I've just made it smaller, so you see it here. What I'm going to do is on this right, you'll see going up the climate model projections for where temperature is going. There they are for IPCC. And you see this line here is 2100. So it's 100 years, and we'll go from about 1.5 degrees up to about 5.6 degrees above pre-industrial, actually above 1960 to 1990, I think. Now look at how massive this is in terms of the limit cycle of temperature for planet Earth, for the Holocene. So this is a huge change that we have to adapt to if we go up here, and the Earth has to adapt to. But the point from a complex systems point of view is everyone assumes that depending on how much greenhouse gas we emit, we'll end up somewhere along here. I don't think that's the case. I think what's going to happen is we'll move from now, we'll certainly move up, almost certainly to 2 degrees. That's where we're committed to going now, might even be a bit higher today. And the worst case scenario is way up there. And I think there's severe challenges for us to even cope with that. We may possibly collapse if we go up that high. Now, what about in between? Can we muddle through? I don't think the Earth may let us do that. And if you take a complex systems perspective, what you'll see, whoops, went too fast there. What you'll see, oh, it's dropped out. Sorry. What you see coming in, no, I don't think it has, sorry. What you'll see is a return back to the Holocene, I'll show you that in a moment, or moving up here. I think the Earth will bifurcate, processes that move it down or processes that move it up. So let me show you what I'm talking about in terms of processes that keep it down toward where we are now. If you look at emissions through time from 1850 to 2000, above this zero line are emissions, that big gray wedge that are burning of fossil fuels. This is all the carbon going into the atmosphere. Less than half stays in the atmosphere. Over half goes into the land and the ocean. From a complex systems point of view, this is the Earth telling us that it's trying to pull the system back down toward the Holocene. It's trying to bring that carbon dioxide out. Typical complex system behavior. But if we raise temperature too much, we may activate some of these so-called tipping elements that you may have heard about in the Earth system. Important ones would be the loss of Greenland ice, loss of Antarctic ice, outburst of methane from the permafrost as it melts. All of these things tend to warm the planet, either through changing the reflectivity or putting more greenhouse gases in. And most of them are triggered at higher temperatures, above 2 degrees. So when you put all that together, this is the slide I thought I was going to get to earlier, so apologies for that. If we keep temperature rise down around 2 degrees or so, and then stop it, the Earth itself may pull us back down toward a Holocene-like state. Okay, that's what a complex system does. It has feedbacks that pull the system back down toward a stable state. But if we go past some point, maybe up toward 3 degrees or 4 degrees, the system isn't going to stop just in here. It'll transition up to a much hotter state, perhaps without any ice on it. And we know that's stable because it's been there before. So a complex systems perspective makes it look very different. It says the Anthropocene could be a short period, a burst of activity, and then a return toward a Holocene-like state. Or the Anthropocene could be a shift to a completely new state of the Earth system, and we could be there for hundreds of thousands or millions of years. So this is why it's hard to say where the Anthropocene is going. We really don't know how the Earth is going to behave. Well, let me conclude then with planetary boundaries, which is a concept developed here in Stockholm by Johan Rockström and colleagues that says, all right, that's our problem. How do we try to keep it in a Holocene-like state? So this is now getting back to the sustainability angle. And that's the list of authors. We put together some 25 or 30 people from around the world. One of my co-authors is actually sitting in the audience here. Uno Svedin was a co-author on that. You may recognize a staff member of KTH is here. Some of you may know Sverker, and so on. But we brought together a global set of scholars to look at this problem, and we published in 2009. We're working on an update now. The concept is simple. We're trying to define a safe operating space for humans that keep the planet in a Holocene-like state. I've spent a lot of time talking about this one. I was just telling you about the 2-degree or above climate change. But there are others: ozone depletion, aerosols, acidifying the ocean, other big element cycles like PNN. This is an important one: rate of biodiversity loss, chemical pollution, new stuff that humans are putting into the environment, and so on. Now, we made a pretty thorough attempt, still an initial attempt, to quantify this. And you don't have time to go through all of this. The point is, we tried to put some solid numbers on most of those. We did 7 out of the 9. But when you look at the last column over here, a lot of these, there's still a lot of uncertainties. We've got to do a lot more science on them. But this is now starting to move to something that policy can use. Now, policy is already grappling with this one, climate change. We suggested 350 parts per million CO2. We're already at 390, which means we've transgressed that boundary according to our analysis, and so on. So when you look at all of these, compared to where we are now, you come up with a diagram that looks like this. So this central part of it is the safe operating space. So for each of these axes, think of an axis coming out toward the edge of the diagram. For each of these, the green shows where we put the boundary. Okay? The red wedges all the way around show where we are now. The good news is we think that for several of them, quite a few of them, we're still within the boundaries, although we're pushing out. For 3 of them, we think we're outside. This is nitrogen. It's hard to read here. The one coming up to the top is climate change, and there's been a lot of discussion about that one. The worst one, actually, we think is biodiversity loss. That's the one coming down toward the lower left, the very big wedge that goes right out to the edge of the diagram. We think it's just so much higher than it really ought to be. In other words, we're losing the genetic diversity at an enormous rate, and that's the diversity that confers adaptation capability in the natural environment and ultimately to us, too. So that was our attempt at describing where we are. So in a nutshell, global sustainability, I would argue, means humanity operates within that green circle in the middle of the diagram. This is where we are now, and a lot of these other ones are headed outwards. So that's our challenge today, is to get the ones that are outside the boundaries back in and make sure the others stay in. Very final comments are, well, how do you do that? I think ultimately it comes back to value systems and perspectives. That's what really drives how our politics operates. It drives what technologies we develop, and so on and so on. Now, the interesting thing about the Anthropocene is, and I think Olsen might have said this or earlier, is that it's really sort of taking off as a concept. And certainly in the scientific community it did very early on, and we've used it for over a decade. But only the last 2 or 3 years has it really become out into the public. And you can see some examples of this just here. That's the French magazine Le Monde. And it actually shows the cultural differences in interpreting this. So the French view things in terms of food, either in terms of love or in terms of food. In this case, it was in terms of food. And they viewed the planet as a nice big pudding or something like this, and humanity is eating through the pudding. That's the Anthropocene. Now, the Americans still have a very different view of the world. So here's the American view. Everything is bigger and better. Isn't this great? We're now in control. This is the Anthropocene, the age of man, in big letters. We're number one now. Forget all this nature stuff. We know how to run the planet. So this is Wall Street's view of that. But of course, you've really made it when you find out you're on the cover of The Economist. And so last year, The Economist decided, well, this really is an important concept. So welcome to the Anthropocene. And if you get inside, you might work out that some clever economists have already worked out how economics can solve the whole problem. So it really depends on your perspective, your worldview as to how you interpret this. This is another view of perhaps the American one. And this was actually published, this cartoon was published in an Australian paper on the 100th anniversary of the Titanic. So it says, don't worry, relax, we're indestructible. That's maybe humanity's view as we go charging ahead into the 21st century. And there's that iceberg looming out there. The iceberg could be relabeled the Anthropocene. We'll just steam right over the top of it because we know we're indestructible. Well, we know what happened in 1912. And I suspect there's still some vulnerabilities out there that we haven't recognized. I think ultimately what's happening here is that science is challenging how we think about ourselves. And that's happened before. This is an obvious case. Evolution, which really challenged a lot of people's beliefs and still does in some parts of the world. The belief that we're somehow special, that we have some right to dominion over the rest of nature, that we're different from nature and so on. But Darwin said, wait a minute, we're part of nature, still are. In fact, we're an ape. We're one of several species of apes, and we have some interesting characteristics. We're very clever. We can use our hands. We've got big brains, but we're still apes, and we're still subject to the laws of nature. And that really shook a lot of people. It still does. The Anthropocene is doing that too. It's challenging our view of at least post-World War II progress, that the ultimate is economic growth, material growth, and that will confer well-being. And people still challenge that we can really affect our global environment. And I feel this a lot when I'm working on the climate change issue in Australia, where a lot of people challenge the notion that humans can't actually affect the global environment. But I think the evidence is now overwhelming, not just in climate, but in many other aspects, that we are. So it's challenging our way of life or our view or many people's world perspectives on what is humanity and where we should go. So ultimately, this, I think, is really what the Anthropocene is doing. I'll close. Just the last 2 or 3 slides are on sustainability. You've heard of the 3 pillars of sustainability that we trade off: economy, social systems, and environment. The Anthropocene is actually telling us it's not 3 equal pillars that you trade off. It's a nested, what we call a nested hierarchy, where environment is the largest and most important. And you can see this by simply relabeling it as I've done: Earth's life support system. It looks very different when you relabel it. It's not something out there that's nice to have a clean environment, but if we have to sacrifice it, we sacrifice it. Not at the global scale. A stable Earth is something we have to have or we can't develop. That's shown, I think that's shown quite clearly in what happens at regional scales when we overuse an environment, societies collapse. Social systems are important. You can't have a good economy unless you have a really good social system. It's not the other way around. You can't build a good social system through economics. It's the other way around. You have to have a good, solid social system, well-functioning, and then you can have a good economy. Look what happened when the Soviet Union collapsed. They collapsed socially and politically, institutionally first, and then their economy went downhill. So that's been demonstrated too. Conclude with this fundamental notion that challenges world's views. We actually have a long history of looking philosophically at our relationship with nature. And the best place to look actually is religion, because that's forced us to think about who we are and how we relate to the natural world. It's interesting, if you go through religions, you can find passages everywhere that have to do with our relationship to Earth. There's the classic one from the Bible, from the Christian religion of hurt not the earth, the trees, sea, and so on. But you can also find it in the Quran in terms of balance and so on, and respect for nature. And of course, the Buddhists, I think, have the most lyrical, without the willow, how to know the beauty of the wind, is a very nice saying about our relationship to the earth. I really like the one from my own country, from Indigenous Australians, because they understood what we call biogeochemistry. They understood cycles. They used the word cycle, the cycle of things, the movement of things through cycles. And the role of humans is to keep the cycles going in a good way. Help keep the balance of nature and the cycle of living with the land. For hunter-gatherer society, that's an incredibly sophisticated understanding and view of humanity. So I'm going to leave you with that, and hopefully I've left enough time for some questions. Thanks very much.